cylinder and derive an equation that tells us about the critical buckling pressure gradient based on our geometry and our material properties. So plugging in the numbers that we have here, we get a pressure gradient of 39 megapascals, and using an elastic modulus of 200 gigapascals from Tyler's trade study, we can derive a diameter to thickness ratio of around 15. So this is good for thin wall approximation if we're between 10 and 20 thin wall periods time to hold. But we'd like to increase this number by developing an internal structure that will be integrated with any shelving that's needed to house the instrumentation. By raising this number, we can ultimately lower the mass that we're taking. From that, we move to designing our main shell here. So we wanted to use a teardrop style in an attempt to keep hydrodynamic properties in check. Beyond that, we want to run our designs through finite element analysis calculations to determine failure modes and buckling modes. And once we do substantial iterations of that, we'll run some CFD calculations to study hydrodynamic properties and alter our design if possible to use those. So initially, when we started this structures concept, we looked at curiosity as a benchmark because it's the only rover currently in interplanetary operation to get constraints on mass and I'll pass it on to Chris and talk about those implications in our ballast system.
Thanks, Nathan. So ballast system, what it simply does is it allows for the additional reduction of mass in a system to allow an object to sink or float. So right here we have a graph which shows a trend between the volume of the ballast ratio and the volume of the rover, along with properties of increasing mass. Right here is our maximum mass 90 kilograms. So when we have a better idea of the mass of the structure and scientific payload, we'll be able to figure out the volume ratio of the entire rover to the ballast system. So when going through the selection, we want to requirements of being simple and be precise. So we have three different types of systems that we looked into. We had a gas operated system, which uses gas that goes to pressurized air to push water in and out. These were the most complex, but they also work the fastest. We also have a pump system, which uses an actual pump to allow water in and out. And then these were like the easiest to construct. And then we finally went to mechanical systems, which uses an actual physical system to let water in and out of the system. And this was the most accurate for the buoyancy controls, and it's also relatively simple, which is why we decided to use a piston system as our ballast system. So this is like a preliminary design of what we want the ballast system to look like. There will be two of these on the opposite sides. Basically, water, when you want water to be filled in, or you have this thing pushed back, water will be allowed in, plus allowing the rover to sink. And then when you want it to rise, you simply have to push the water out, thus reducing the mass of the cross. And now we have James, Sean, and then Joe to talk about controls.
Hi, so for the Uvee control team. So a quick overview. Our job is to investigate a way and design a way to control and communicate with a rover that will go beneath the ice and possibly into supposed water on your rover. So a couple of things to keep in mind when we're doing this include underwater communication, which consists of either we do tethered or untethered communication, and then keeping in mind the possible ranges we can get with those different kinds of communication. You have to keep in mind movement control, such as how we're going to take the commands we send to the rover and turn those commands into actually moving throughout the rover. And we have to implement certain levels of autonomy, ranging from simple task automation to advanced automation. So here's some of our milestones and objectives. The first milestone is to just establish a remote connection with the rover and control the rover remotely. We would like to then implement a semi-autonomous algorithm to help it control its position, and then implement a fully autonomous algorithm to help it control its position and its So to accomplish these, we've got some requirements. The rover, we have to communicate with it over a range of 10 kilometers while losing no more than 5 decibels of signal intensity. The system must not exceed 50 watts of power consumption. We have to be able to validate the integrity of the commands we send the rover. It's going to move along the x-axis and needs to be able to detect any potential collisions in the position. We must know its orientation and position with respect to the base station, and using that, we have to figure out its maximum transmission range to the base station. We then want to be able to minimize power usage when it enters sleep mode, and while it's in sleep mode, be able to maintain stability. So we've got a few options for communicating underwater. As far as wireless control goes, we can look at radio waves, which have a very high attenuation rate, and also a very high data transfer rate. And then we can look at acoustic waves, which have a very low attenuation, but a very low data transfer rate. We'll touch more on this in a few minutes. And then tether control. So this requires a very, very large amount of fiber. While it does have a very high data transfer rate, it's very, very heavy, and it have a very large volume. It's very high transport to the rover. So I'm just going to pass it off to Jonathan, who's going to talk about attenuation of radio waves in water.
As James mentioned earlier, we required that our rover operate up to 10 kilometers away from the base station with a signal degradation of less than 5 decibels over that distance. And so that leads to a maximum attenuation rate, a maximum tolerable attenuation rate of 0.5 milledecibels per meter. Now, the attenuation of radio waves of any electromagnetic wave water depends on both the conductivity of the water as well as the frequency of the wave that transmits through it. This diagram is from an article that appeared in a amateur radio magazine in 1987. As you can see, the attenuation of radio waves increases both with frequency and with conductivity. Now note that our required 0.5 milledecibels per meter attenuation rate is far lower than the 0.1 decibels per meter indicated on this graph. This means that we would need to use very low frequency radio waves if we were to use that. And so this leads to one of 3 possible options. One, since we are using very low frequency radio waves, it means that the wavelength of our radio wave that we use to communicate needs to be very long, and thus we would need to have an impractical direction to. Alternatively, we could look at the range of the rover, and this will force us to go below our 10 kilometer requirement. Finally, and this is the option that we're looking into, is we're looking to using acoustic waves to communicate with the base station. This will allow us to bypass both the attenuation problem and allow the craft to stay operational at 10 kilometers away. The issue with this is that it comes at the cost of lower data rate. Now this table shows the attenuation and therefore the range that our rover can operate at, as well as the data rates afforded by these 3 options. As you can see from the acoustic and radio waves, there's a trade-off between attenuation and data rate, and therefore a trade-off between the maximum range of our rover and data rate. Obviously, if we use fiber optic communications, none of this would be an issue, except for the fact that the tether would need to carry, as James mentioned, would add mass and volume to our payload. Now I'll pass this back on to James, who will talk about our investigation into using acoustic.
Thank you, Jonathan. So there's a few factors that contribute to intensity loss. With acoustic communication, those being salinity, temperature, depth, and frequency. Of those, depth is the most important factor in determining the frequency for desired range. So something to keep in mind is that acoustic waves are compression waves. They move like this. And compressional waves cause pressure variations in the media that they are traveling through. These pressure variations can cause molecules to disassociate and thus absorb energy from the waves traveling through. And this is the biggest factor in trying to determine the attenuation of a wave through a given medium. So We can show here in this graph that the attenuation, like in the Atlantic Ocean, you can see as frequency decreases, the attenuation decreases as well. So this means that in order to get the largest range as possible, we want the attenuation to be as low as possible, so we want the frequency to be as low as possible as well. So I'm going to hand this off to Joe now. We're going to talk about vehicle control.
Thank you. Now I'll present to you two plans for controlling your vehicle. The first one includes one large propeller on each side. Those two propellers will be able to tilt up and down and change their angles. The second plan includes one large propeller back and one small propeller on each side. And those two small propellers will also be able to change their angles. Those two graphs show the movements of the rover if you take the second plan shown in the previous slide. On the graph, you can see that the dots and arrows represent the propulsion directions, and the actual arrows represent the movement of the rover. Clearly, the rover will be able to move forward, to left, and right, and then we adjust the angle of both right and left propellers. You can adjust the depth to up and down. Now that we have seen the basic movements of the rover, the best way to understand how we can manipulate those movements is to see it avoiding an obstacle. To avoid an obstacle, first we should be able to detect the minimum distance for your vision. Second, it will determine the most efficient way to maneuver around the obstacle. Now, in this example, we can see that the obstacle is directly in front of the rover. The rover can take the strategy of first using the right propeller to push to the left, and then you will use the back propeller to push forward to a point where you can use the left propeller to adjust back to its original direction. Now I'll pass it to John to talk about an investigation of how we can actually control those movements.
Thanks, Joe. So, as you mentioned, I will be touching on more of how do we control the rover, or rather, how do we get the rover to control itself and autonomous algorithms. So, we implemented a kind of first step project to just get an idea into this whole idea of controlling this rover. So, imagine a two-dimensional vehicle moving in the XY plane, and these LEDs represent 4 jets that comprise this propulsion system. The intensity of the light supplied to the LEDs represents the amount of power supplied to the said jets. And we use the Arduino to conduct this experiment because it's great for prototype and it's easy to learn and low power consumption. So anyways, here is a controller that we made using processing, which works together with the Arduino environment. We can see a cruise control pad and boost control pad, and adjustments on cruise speed and boost speed, which are displayed between them. And the cruise speed is set to a level where you can toggle on jets to a specific speed. And the boost speed is toggled as well, and when activated by buttons representing each jet 1, 2, 3, 4, and where the core buttons activate each adjacent jets, it will go from its initial power level up to the boost power level, down back to the initial power level, if it was on, or the cruise speed. In very split seconds, so it just it's very useful for them. So just some pictures to represent this. Just 3 and 4 toggled on. We could have acceleration at 71% max power. Quite right, a little hard to see, but in comparison to this next picture, where it's only 2% power, you can see that it's much less intense. And this just includes to us that it is possible to manipulate these basic functions of an imagined vehicle and process them. So now I'll pass it on to Seth to talk more about propulsion.
So for the propulsion of our vehicle, the main task is to just kind of determine what sort of method we use to propel this vehicle. And in the feasibility stage, what we're investigating is where we're going to put the thrusters, so where all the propulsion methods will be, what the motor is going to look like, so how it's going to be waterproof, how we're going to make sure we have the right torque and speed required, and kind of characterization of the propellers that we do. So our only real milestone for propulsion is that all the systems we propel the vehicle. Basically, it has to allow for turning or straight movement on just the body fixed x-axis as fast or slow as you want it to. And importantly, it has to use minimal amount of power because we're limited. So the requirements for this are it has to be able to turn about the z-axis, so just level turns. It has to move up to 1 meter per second relative to the water current. So this means that it will be able to move faster at slower currents, but we don't need to get anywhere in major. It has to use less than 50 watts of power, it has to be completely waterproof, and it has to withstand extremely large pressures. So what about kind of characterization of the thruster locations? Configuration 1, kind of touched on, Joe was talking about controls. It basically involve a large propeller on the back and 2 small propellers on the sides. This would use differential thrust for steering, and would use angling those propellers in order to change the depth at neutral velocity. Configuration 2 would be just one large propeller on the back, which would implement thrust vectoring to change both the pitch and to perform trading operations. And configuration 3 would just eliminate the large propeller, instead have 2 propellers on the sides to provide both the main thrust and trading operations. So for motor characterization, we had to investigate what the best option would be for a waterproof motor. We don't want the electronics bay to interface well with water. For this reason, we're going to use a magnetically coupled motor most likely. And basically what this is just you have a shaft attached to a magnet, and by changing the polarity of the magnet on the inside of the rotor, you can actually create a torque on the shaft, which will be attached to the product. So for propeller design, in the feasibility stage, again, we aren't doing a ton of design as far as numbers, but looking into what we'll be doing going forward with the rest of our prototype and conceptual design, we'll be using OpenProp, which is a MIT MATLAB software, and we'll be able to plug in our values for what we want the propeller to do and analyze how the efficiency change based on different parameters. Now I'll talk about power of the rover, both the conceptual and the prototype. So our task for power is to create a system which powers the instrumentation, but also has to power heating the rover, propelling the rover, and communicating, which are all rather large power sources. So our milestones for this are we have to design a power system for the conceptual vehicle, and then when we're moving into prototype design, we'll have to design a separate power system for that, just based on differences in power from solar. And the requirements for this that we have to provide up to 100 watts of power for the vehicle, has to operate for no less than 5 years, can't have a negative environmental impact on Europa, we don't want to kill all life on Europa, and has to maintain a safe internal temperature for growth. So some of the options for our concept vehicle are to use an RPG, a radioisotope thermal electric generator. Basically what this does is it takes radioactive decay of plutonium or another isotope, and turns that into energy. A couple other options, which a nuclear reactor. There are a couple spacecraft which implement this. It does provide hard power, but at the cost of posing larger environmental risks. You cannot really justify it. And then there are non-nuclear power sources are kind of eliminated. Just we don't have solar power under the ice, and current generated power is rather inefficient and require a lot of engineering systems and large mass. So just a little bit of heritage of RTG. The first option that we discussed. On Curiosity uses currently an MMRTG. It's 45 kilograms at 510 watts, which fulfills our power requirements. And it lasts, we're predicting up to 14 years for Curiosity. Looking at the heritage of RTGs used in the space industry, almost all of them have survived their predicted lifetime plus a couple of years of sent to Voyager missions, which are still working out to 30 plus years. So when using this, this kind of leads into the environmental impact, but an RPG will typically use plutonium-238. And this is obviously it's a radioactive material. It is an environmental risk, but at the same time, if you compare it to some of the other potentially less dangerous materials, the half-life is significantly greater, and so it would give us a much longer lifetime. And when you go into environmental risk, there are many safety precautions that are taken in the design of an RPG.
Generally, you'll store the plutonium itself in smaller compartments within the RTG, and then it will be protected by a layer of iridium and encased in graphite box. So there's a lot of engineering going into making sure that there is not a leak in the first place. And a couple cases where we've had problems in the middle of the launch. The transit navigation satellite was kind of a predecessor to UBS. And one of these burned up on re-entry on failed launch. And it did need some plutonium, so it kind of shows that there can be something really wrong with this. It was not a major disaster. Whereas Apollo 13 was kind of obviously one of the worst case scenario re-entries that we encountered in space exploration. But the RTG, which ended up landing in the Pocket Trench in the Pacific Ocean, is still intact. We've done studies, or we haven't, but NASA has done studies to ensure that there's no sign of any environmental impact. So I'll probably talk a little bit about the future work of the project and where we're going to be going the rest of this year and this semester.
Yes, sir. Okay, so I'll just go through the presentation. So for the rest of the semester, we're looking into finishing the concept design. And that's not, of course, it has to be done. There's a lot to be involved in with here, but we always aim towards finishing the concept design as soon as possible. And then move from this first goal to the last one, which is actually form laboratory experimentation. So we want to make sure whatever we hypothesize that we will actually work in play. So that's what we're moving for the rest of the semester. We're trying to make sure all the systems, from structures to control to science, they at least have some sort of lab experimentation building. For summer 2015, we're going to try to spread. We're not actually sure if we're going to do our own number, but some of us will be working a role for the projects, and more people actually welcome to stay and do work. So we're going to see as spring what we can get for the summer. We're most likely trying to get more hypotheses and theoretical work for the summer. And then fall 2015, try to aim to get a complete design prototype. So actually a system fully integrated and fully capable, at least in design, to work and start building the prototype phase. But by building, we're not suddenly we're going to have all the two parts. So I felt like we're not going to be able to get an RT, right? But we can get close enough. That would be the idea. And then for winter 2016 and spring 2016, move towards the final design, which is pretty much the idea of having what we have right now and what we're going to have at the end of the year and optimize it to get better and better results for the robot. This concludes our presentation. I'm more than happy to get questions if you guys have some. Yeah, thank you so much for coming. Questions? Oh, what's up?
You guys are talking about 10 kilometers of base station. With that, is that, I guess, is the goal?
Yeah, so the problem, so here it is actually a good question. So there's a lot of discussion if we're going to have a rover, we need a lander or not. But, the problem here is you can simply send your data through ice. So, yeah, so theoretically we have to have like a gas layer, then you have a hole, then you can do that would be water.
So if you have something in the top device,
Yeah. So that's the thing. You need to have some sort of thing here, and that's what we call a lander. So we'll always assume if you're gonna have a rover in a rover, most likely you're gonna have satellites orbiting, right? So you can either have some sort of like just a simple gadget or instrument there connecting the ground, the ice to the satellite, or you can have a lander. So whatever works better. But then if you have a lander, then you need to optimize the rover much better so it's smaller and actually fit the same field all the way.
you guys just working on just the order.
Yeah, yeah.
There are a lot of components outside of just the lander. How we're going to drill through the ice, which makes a really broad project. And at least to start out in the feasibility stages, we're trying to keep it a project that's somewhat feasible with people we have. Going forward, hopefully at some point we will start tackling some bigger questions as far as how we're going to do this. But as far as beginning of designs, what we're assuming is we're going to add the landing. The drill will probably be integrated with the station on the bottom of the ice, but that's what we're gonna use for our operational base station.
Because one question you have to answer here is, if you want to figure out science in Europa, what type of instrumentation you need to have in order to do so. And that's why I figure out the size of the rover. So after you have the size of the rover, we'll be like, okay, we know the size. That would be a nice implementation setup. Now we need to send it to rover. So what we need to do, how much you need to shrink this current design to actually get something.
What's the traceability of that 10-kilometer requirement for like a range? Like, is there a scientific reason as to why you chose 10 kilometers?
So, you back to the slide of the attenuation, sure. So, so in general, attenuation looks something like this. This being where you're at the surface, which corresponds to being here, up there, depending on your frequency. So what actually happens is you find out that up until about 10 kilometers, the maximum attenuation occurs at the surface. After that 10-kilometer mark, it just starts increasing and increasing and increasing. And there's not really an upper bound to it. It just grows and grows and grows. So that means that we're going to broadcast a signal back. The minimum attenuation is going to be where we're at, wherever we are. And we know the maximum attenuation is going to be up here. It makes our calculations a little bit easier. And so we were trying to figure out how far we can go and still get accurate, good data. And 10 kilometers is pretty gosh darn far.
I guess my point's more, why go 10 kilometers if you don't have a scientific reason to go 10 kilometers? Like, if you can get data within, say, 50 meters, and you can just have a smaller tether.
I see your point. So,
Because it can just, it
Yeah,
has
no.
a system.
that's a great question. And, I mean, so what James is describing is actually engineering this question. The thing in Europa, we're assuming that the water layer is going to be somewhere from 100 to 200 kilometers, right? We're actually not sure if we're going to go to the deep regions of Europa and if we're just going to stay in the shallow area. So 10 kilometers would actually be a good start, but you could go deeper if you want. And if you want to reach the silicate area like before, you need to get at least halfway there, which actually sets some sort of sign. So 10 kilometers is a start.
Yeah, my main concern is like that's a pretty big driver for a lot of the system requirements, and just to have like a
You need to
strong,
research that. Yeah.
yeah.
That's for sure. So the thing is now optimizing the scientific ability. How you can get data in like staying to like 5 kilometers or 6 kilometers or 10, which is the middle, and then do all the science you need from there. And, but at the same time, you want to do some sort of experimentation with the ground. You have to figure out how to do it. It's a fairly big question.
We also, we aren't entirely sure what it can look like. If there might be currents that we're not expecting, just unpredictable factors where if we do end up being carried a significant distance away from our base station, we still want to be able to communicate within a very decent range.
Yeah, no, that's fair. I wasn't speaking primarily for the communication side, but just in general, it's a mission requirements. Yeah.
Also, because we have our range we set for so far, we designed for that. It doesn't become a limiting factor. So also, if they want to design the shell to go 10 kilometers, it doesn't make that 10-kilometer range a limiting factor. Whereas if we set 5 kilometers, then we have to design it for 5 kilometers.
Awesome. Thank you so much for coming.
Yeah,